Okay, so here are the notes for 6.3. We're going to talk about the central limit theorem. In statistics, we often talk about individual data values, like what's the probability of an individual being selected and their height being above 5'6", or things like that, about individuals. But often we also want to know about what's the likelihood that when we take a sample of people, that their average of that sample will be above or below the average of an individual. And so we want to talk about the central limit theorem, which allows us to talk about that relationship in a very clear and concise way. When we sample a distribution of any statistic, that sample, the sampling of that sampling distribution will be normal or nearly normal if the sample size is large enough. And here are some characteristics or conditions that must apply. When the original variable, maybe it was your IQ, is normally distributed, the distribution of the sample means will be normally distributed for any size. When the distribution of the original variable might not be normal, maybe it's the average household income in the state of Idaho, that may or may not be normally distributed. And if it's not, we can fix it by taking samples of at least 30 or more, okay? And if we take samples of 30 or more, we're going to get an approximately normal distribution of sample means. Now, the original data still isn't normal, but the means of the sample are normally distributed. So one other thing that changes when we deal with this sample, right? We're taking samples of 30 people, and then we're getting the average of those 30 people. That's called a sample mean. Now, if we want to talk about those sample means, how they distribute, while they are normally distributed, they will have a standard deviation that is slightly different than the standard deviation of the individual data. If the standard deviation of the original data is sigma, we will need to divide that by the square root of the number of data values that we're taking in our sample. So if it was 30, it would be the square root of 30. If it's 50, it's the square root of 50. That's whether it's normally distributed or not. The sample means have this standard deviation. Now, when we do that, if we were to sample all the possible ways we could compute, the means compute from all the possible random samples. So if I'm taking 30 people out of a population of 100, there are a lot of ways I could select that 30. It could be the first 30 in the alphabet. It could be the last 30 in the alphabet. It could be every other person in alphabetic order for the first 30 that I draw. So that'd be 60 people. There's a lot of ways I could do this sampling. But the reality is there's always a chance that sampling isn't perfect. And if that sample that I have is not in line with the actual representation of the population, we have what's called a sampling error. That sampling error is the difference between the sample measure and the population measure we would expect to have. So the average height is 5'6", for some reason in the class there's 5'6", and the sample we take is 5'5", the sampling error would be that 1 inch, okay? And so we know that not everything is perfect. If we take samples over and over again of the same size, n, the mean of each sample over time, as we take more and more of them, the sample mean, okay, mu x bar, the mean of the samples, will equal the population mean, so that mu and mu x sub x bar, mu sub x bar, they become the same value. That is to say, if I take enough samples, yes, some of the samples will have a high average, some of them will have a low average, but they should all average, the sample mean should average out to be the population mean, if I do enough samples. The standard deviation, sigma x bar, this guy, is always going to equal the standard deviation of the original population divided by the square root of the number of data values, or the sample size is what it's called. So our Z formula changes when we're talking about a sample. So this is the Z for a sample, whereas for an individual data point, we would go back to what we were doing before, where Z was X Notice, on the left over here, we have the mean. X with a bar over it is the sample mean. Here, we're talking about a specific value. So it's not an average. It's just X minus the regular mu divided by sigma. This would be for an individual data point, like we did in 7.1 and 7.2, or 6.1 and 6.2. In 6.3, we're going to use the sample mean, which means we're going to have to change the sigma, is really what you're going to see the change in. Let's do a couple examples and see how the central limit theorem can help us solve these problems. We've got an example where that reported that children between ages 2 and 5 watch an average of 25 hours of television per week. Assume that it's normally distributed and the standard deviation is 3 hours. Because it's normally distributed, I don't need to have 30 or more people in my sample. But I do have 25 hours, 3 hours is my standard deviation. And then in the sample information, right, so that was general information. Now I'm going to sample 20 children, and I want to know what's the probability that they will be greater than 26.3 hours. What's the probability that someone's going to be, and that sample will be higher than that. And so the first thing that we're going to do is we're going to adjust our sigma to be the sigma of the means. So the standard deviation of the means will be the standard deviation of the whole, which is 3, divided by the square root of the sample size, 20. And if we put that into our calculator, 3 divided by the square root of 20 gives me 0.671. We'll call it 0.67. I'll go 0.8. I think 0.8 will work fine. Yep, 0.8. So there's my new sigma. Now when I draw the normal distribution curve, we're not talking about all of the individual data values. We're actually talking about the separation of the means. Now, if I do enough samples, the mean of the population will be the mean of the samples. So 25 still goes right in the middle. And we're worrying about being greater than 26.3, which would be the right side from 26.3. To figure out the probability that X bar, that the mean of my sample, is greater than 26.3, I need to find the z-score for 26.3. So to do that, I take my number, my mean that I'm focused on, 26.3. I minus the mean, the average, of 25. And I divide that by sigma over the square root of n. Now I could type that in now, but I already did this calculation. It was the 6708. You're going to have to do the top and the bottom separately. So whether you pre-calculate the new standard deviation or not, it's up to you. If I throw this all into the calculator, again we got 26.3 minus 25. We're dividing it by 0.6708, 1.94. Z is going to be 1.94. Now remember, because I'm looking for the right side, I either have to do 1 minus the probability on the table for 1.94, or because I want the right-hand side, I could switch this to negative 1.94, which would move the line over to here. And think about it, this space to the left of this is the same as the space to the right of my 1.94. So I'm going to use the negative 1.94 approach on my table. Am I on the negative table? At negative 1.9, I slide over to 4, it's 0.0262. So the probability of being greater than that is 0.0262. Not a high probability. Mostly it's like a 2.5% chance, not very likely. Most kids are going to be under that 26.3 hours. Okay, same idea, but we're doing it for a vehicle between two values. Since the sample is 30 or larger, because we're doing 36 vehicles, we don't need to worry about it being normal. It could be a normally distributed data, but it doesn't have to be. It says that the average age of a vehicle is 96 months. The standard deviation is 16 months. We're going to sample 36 vehicles, and we want to know what's the probability of them being between 90 and 100. So a couple of things to figure out. Let's draw our normal distribution curve first, our bell curve. Right in the middle should be 96, and we're trying for between 90 and 100, so that's the middle. So I'm going to need the z-score for 100 and the z-score for 90 so that I can subtract them. And this is the value of interest, 100, minus the mean, which is 96, divided by, and I'm not doing 16. That's not the standard deviation. The standard deviation of the means will be 16 divided by the square root of 36, because that's my sample size. And I can do the same thing with my 90 minus 96 over 16 divided by root 36. You either have to put parentheses around the top and bottom, or you're going to need to calculate the top, the bottom, and then do the division. Be careful not to get lazy here. So I'm going to go ahead and just use parentheses. 100 minus 96 divided by parentheses 16 divided by, the square root of 36 is 6, so I'll just type the 6 and be done. I get 1.5 here. And if I do the other one, 90 minus 96 is a negative 6 divided by parentheses 16 divided by 6. Again, the top is only one number because I did the math already. I get a negative 2.25. So now I need to go to my table and find the z value, or the probabilities for 1.5 and negative 2.25. I'm on the negative side, negative 2.20, 1, 2, 3, 4, 5. I believe, yep. I'm going to be at 0.0122. So for this guy, 0.0122. Was I doing that right? Sorry, you got to make sure these things are right. 0.122. Okay, and then I need to go to a positive 1.50, which will be this number right here, 9332. So this one here produces 0.9332. And because I'm doing the middle section, it's the right value minus the left value, so that I only get the in-between left. So if I subtract 0.9332 minus 0.0122, I get 0.921, or 92.1%. All right, guys, hopefully that will help you get through what the central limit theorem is, but really what it comes down to is instead of looking at individual values, we're talking about sampling and comparing that sample. So keep that in mind as you go through the process. All right, good luck, and we'll see you in class.